Today we get to talk about dynamics, and the goal is simple. I want to make sure you understand some of the fundamentals and have some of the definitions that we'll be using throughout the class. I want to get a little specific about talking about stability and what that means in nonlinear systems, and give you some graphical tools to think about it. But the unwritten goal, which I will state, is that I'm trying to make you love dynamics, right? You're not just, it's not enough to know it, you have to love it and realize that it's like the right way to think about everything you see in the world. So, I don't know how to test that on a problem set, but we'll do what we can. I'm going to start really simple. Simplest robot I can imagine that does something interesting is just a simple pendulum. And we're going to actually, we're going to understand a lot about the pendulum by the end of the lecture, but I'll try to convince you throughout this lecture and the next few lectures that it's a really relevant exercise. In fact, robots are mostly just a few pendulums put together. So let's start with the simple pendulum. Quick vote, is this or this better in terms of color? More readable? White. White's better? Okay, it's smaller. So I will use it as long as I can. All right, simple pendulum. Mass, length, gravity, angle theta. The word simple just means that I've got a point mass. That's not some canonical definition, but most people, when they say simple something, it's a point mass version of the model. Okay. So we can do exactly what we did last time, write the kinetic energy and have m L dot theta dot squared. Kinetic energy, potential energy. Now it's negative mgl cosine theta. Put it into the Lagrangian, take a few derivatives, and the thing that comes out is an equation that is probably familiar to you. You will certainly use it a lot today. You get out ml squared, theta double dot, plus mgl sine theta equals whatever our generalized forces are. So we'll call them Q for now. Any additional generalized forces. This captured the gravitational potential, but if there's anything else we want to put in there, we'll put it in there. In fact, we'll go ahead and put it in. So let's say for today, the ones we'll care about, we'll think about having some friction in the joint. So we'll say that there's some damping, just linear damping. So on this side of the equation, it's going to look like negative v dot. It's going to slow me down proportional to my velocity. And then maybe I have a torque input, which I'll just call U, because if I have a motor applying torque at the base. Okay, so focus on those equations or variations of it for a few minutes here. And just to write that all in one line, that sums up to being ml squared theta double dot plus b theta dot. I move that to the other side, plus mgl sine theta equals, sort of a classical form. You see those on the left-hand side. All right, this is, looks like a good old 1803 exercise. Standard differential equation. It's a second-order differential equation, right? The dots are big enough, I hope. Second derivative, first derivative. So, what are you doing with differential equations? I should be able to ask you a question like this, right? So if I say, given the initial position of the pendulum at time 0, and the velocity of the pendulum at time 0, then you should be able to tell me what, you should be able to answer a question like this, right? Where is the pendulum at time, whatever time I ask you, right? Standard differential equations right out of 1803, almost. So here's the rub. It's not out of 1803 because there's a sign there. It doesn't look like much, but there's a sign there. And there is no closed form solution to this, right? We just suddenly, just by virtue of having that sign theta in there, we fell off a cliff. And it's not just that I haven't learned it yet or something. It's that there is no closed form solution. Sort of even if b is 0, you get into elliptic integrals of the first kind. And when b is non-zero, I don't know. It's not useful at least. So so there's not a lot to be. This is sort of the classic view of differential equations, but it's not the right view for what we're trying to do, right? So my point is that this is good, but it's not the question we often care to find the answers to. So if that's the wrong question, then what's the right question? So it depends what you're trying to do with your pendulum or autonomous car drifting or whatever system under consideration. But oftentimes the goal is not to understand exactly the position and velocity of the system in space at a certain time in the future, but it's a more abstract goal. Like, I just like to know roughly where this is going to be as time goes to infinity, right? I'd like to know if it's down here or if it's up there, or if I threw it out the window, which I almost did once in an old lecture. That's why I've got software demos now. And, if it's an autonomous car, maybe what I care about is it ever going to visit a state that I consider to be bad, that's off the road, or something like that, or in collision with another vehicle? These are questions that you can potentially answer, even though you can't answer this question. And that's going to be a key idea here, is that solving the differential equation explicitly is not a prerequisite to understanding a lot of things about the system. Okay, so for instance, the simple one we'll think about here, which is stability, is about asking the question, what happens as t goes to infinity? That's a good question. That's the one we'll know a lot of answers to, right? For the pendulum, you probably have a pretty good guess, but we'll make sure you really know deep down why it is that way. There's a bunch of ways to do it, and the ways to do it depend on the system, the types of equations you've got, the number of the dimensionality of your state. All these things matter. But the way that's going to make you love dynamics, I think, is the graphical way, which I can only do for very simple systems, but graphically everything is just beautiful and good. So let's do some graphical analysis. There's actually a great book by Steve Strogatz on nonlinear dynamics and chaos. If you haven't seen that and you like this stuff, there's more. To read Steve Strogatz's book. His book is where I first learned about graphical analysis and really loved it. So, okay, but to make the graphical analysis even simpler and even more penetrating on this particular equation, I'm actually going to have to make it simpler still. This is still a second order system. I want to make it look more like a first order system. And there's classical understanding in dynamics about how when first order analysis is suitable for a second order system. You could think of it as sort of the heavily damped regime. In fluid dynamics, it would be the Stokes regime. It's like when you're moving through molasses or something like this, the high damping regimes. This is the cases where the inertial terms really don't matter, and the velocity and viscous terms dominate. So what does that mean for a pendulum? That means I want my velocity-related terms to be much bigger than my inertial terms. If that's the case, then I can kind of ignore this for now and then bring it back later. So, we want some somehow the terms b theta dot to be much, much bigger than the inertial terms, the ml squared terms. If my dots are not big enough for the back row, someone just shout. Okay, but I wanted to make sure you think about dynamics in well, a little bit like a dynamicist today. So this is not very satisfying because this is a state-dependent observation. So somehow I want to just make a statement about b and nl squared, my parameters. Are my parameters are in a regime where I could do first-order analysis? So, well, here's the question: what are the units of b? That's kilograms, let's say. That's meters. What are the units for b?
4 seconds per meter.
Sure. So just to keep it more analogous to this, can I call it kilograms, meters over a second? Yeah, good. So these terms have to have the same units over here. They have to be coming out as something that looks like torque. So what he says is absolutely right, but just to make the analogy super clear here, let me write it as kilogram meters squared over seconds, right? So it's almost, I've got one derivative coming from the time here, 1 radians per second, but everything else is stuck in b. That's my units for b. And ml squared, of course, is kilogram meters squared. So the thing, if I want to compare b and ml squared, I need something that, in my dimensional analysis, relates these units to these units. All right, there's this whole field of dimensional analysis. So I need some characteristic time constant to just relate the units of this to this. And for a pendulum, there's a very natural choice. If the undamped pendulum certainly tends to swing at its natural frequency, right? So so there's a natural relationship in that natural frequency between theta and theta double dot, theta dot and theta double dot, and I can stick that in basically to cancel out these terms. So the natural frequency is square root of g over L for a pendulum. I want 1 over that. So long way of saying, I think I'm happy if I have b square root of g over L much bigger than nl squared. That in most cases, for most theta dot and theta double dots that my pendulum will undergo, it's safe to assume that this term dominates this term. Okay? And you could have gotten that from just looking at units and realizing you needed to add a fundamental time constant, a characteristic time constant in my system. Okay, so if I'm in this regime, this is my heavily damped regime. My pendulum moving in molasses regime. Then say it's okay to say theta double dot plus b theta dot is nicely approximated as b theta dot. And having everything else move to the other side. And say, let's take a minute and think about this equation first. This is a version of a particular parameter regime for the simple pendulum. And even to make one of it, you wouldn't think I could make it even simpler still. I'm going to leave the sign in. That would be as long as I leave the sign in, I'm not offending my own preferences here. But the one last detail that I just don't want to worry about right now is the fact that theta wraps around itself on 2 pi. We'll push that. We'll come back to that. That's fine. But let's just say, forget about wrapping, and just to remind us that we've made that assumption, I'll replace theta with x.
Cedric?
Yeah.
Should it be L over squared L over G for the units?
So I think that the time constant is square root of L over G.
Yep.
So yeah, you're right. Let's see. It's true. I wrote it down upside down here. Good call. Thank you for correcting that. Always call me out if you see something like that. Okay, so here's a first order nonlinear dynamical system that we can understand everything about, really everything about. The reason we can understand everything about it is because I can draw it in a 2D plot. Okay, so let's plot the function x versus x dot. Is that too high? Okay, I'll draw it even for u equals 0 first. That is just a sine wave, right? It's negative mgl over b sine theta. So negative sine theta looks like it's got a slope of 1 at the origin, sine wave, right? And it's a sine wave that has an amplitude of mgl over b. Yeah? Okay, now by inspection, I can tell you everything that this pendulum is going to do, the overdamped pendulum. First of all, I know every time that the plot crosses the x-axis, the x-axis here, that's a fixed point of the system, right? So this, every time that I cross the axis, these are fixed points, which means it's defined literally as x dot equals 0 here, and I'll often refer to fixed points as x star, let's say. Okay. So if the system starts here, it'll stay here forever. Starts here, it'll stay here forever. Right? The cool thing is I can see much more from this plot. I can instantly say something about the stability of those fixed points. Okay? So what happens if I'm over here? The velocity is positive, so I'm going to move, x is going to move that way in time, over time. Right? If I'm over here, the velocity is negative. It's going to move that way in time, and so on and so forth, right? So I can instantly see that this fixed point is a stable fixed point, right? And this is an unstable fixed point, and this is a stable fixed point, and so on and so forth. So from visual inspection, I can tell you for any initial condition, I can instantly tell you the answer to this question. What happens as t goes to infinity, right? I know that for this set of states, everything in here, not including that line, the answer is, where is x going to be at time goes to infinity? It's going to be there. And this set of states, it's going to be there. Right? So this region here is called the basin of attraction. Or region of attraction of the fixed point. Fixed point x star equals 0. In fact, these areas where the fixed point changes to the basins of attraction, the sets here that define the boundaries of the basin of attraction have a name too. Those are called the separatrix. So, super simple to see on the 2D plot, but I want you to start thinking ahead. Now I've got a robot doing a backflip or picking up something on the table. Maybe these same exact ideas are going to apply. I can ask about the long-term performance of my drifting maneuver my Pershing aircraft, okay? And I'm going to use the same language about stability, about basins of attraction, about separatrix, okay? But here we can see everything. Graphical analysis is very powerful in general, right? So there was anything that is any first order system, I can draw on a single variable. I can draw like this. It didn't have to be assigned for me to plot it and understand everything about it, right? I could have picked any system. So I thought I'd pick today a neural network, a recurrent neural network. Okay. Now, recurrent neural networks are all the rage. Most of the time they're deep. I'm just going to do one neuron, okay? But it's still a neural network and it's recurrent and it could, yeah, hopefully it's a fun example. So let's do a very simple recurrent neural network. And I want to motivate this because I did my PhD with a neuroscientist in brain and cognitive science. And he studied this system. It's called, the particular version of it we'll write down here is called AUTAPS. And it's become an important model in neuroscience, right? So it turns out, we don't know if there's AUTAPs in the brain. And AUTAPS is a cell that makes connection, a neuron that makes connections only to itself. It's a single neuron. And the way you get AUTAPs for sure is you pluck one out of a brain, you bring it sort of on the verge of death, you put it into a petri dish, and you nurse it back to health. And the poor thing it connects to itself, right? And it just sits there in the dish. It grows its axons and dendrites, and the only thing it has to connect to is itself. So it lives in its own little world, and there's some sort of cool pictures here. I can show you what these things look like. So this is a picture of an AUTAPS with dye injected so that it's not that color in your brain. But, right, so you can see that it's living in a dish, right? It's about a big dish with the neuron cell body there. And it's got lots of processes going around that are sending impulses and it's connected to itself, okay? The cool thing is, the reason why this is interesting is that it actually exhibits a lot of fundamental dynamic behavior and has been proposed as maybe a fundamental mechanism of memory in the brain, right? So the paper that went along with this, actually the pictures are more recent because imaging technology got better. But if you could see this, it's big enough, right? Right? The simple illustrations of short-term analog memory storage by tuned synaptic feedback. So you might know the term long short-term memory from neural networks, LSTM. This is the precursor. This is just short-term, but you'll see why, because we'll be able to understand everything with our graphical analysis. It's a hypothesis about the way that the brain might be storing information. Okay. They're cool systems. The way that you investigate them, right, is you take an electrode. First you take a glass pipette. You bring it down to the cell body of the neuron. You try not to poke too hard because then it doesn't go well. You bring it right up to the very edge, right, and then you actually suck on the glass pipette to bring the cell wall a little bit into the neuron, and then you reach down with the electrode. You pop into the neuron in order to get your electrode into the neuron and be able to measure the membrane potential across the cell, and you can start doing all these amazing recordings and start making models of real neurons. Okay, so the system is called the AUTAPS. The standard neuron models there's all kinds of levels of detail of computational models for neurons. Some of them are spiking, some of them are just sort of firing rate based. We'll use one of the simpler ones here. But a canonical neural network model would be that I've got a bunch of inputs coming into a neuron. Maybe those would be my, in our language, my inputs 1, 2, 3. It would be a whole vector of inputs. I've got the neuron has a particular output. In general, I'd have a lot of neurons. And then somewhere in the middle here, you've got some nonlinearity that's maybe oftentimes it's a tanh function or a logistic function, right? Something that makes sort of a sigmoidal function here. It's a nonlinear function of the inputs, maps to my output. The taps is almost exactly this, where I'm just going to feed the output right back as an input. Now, I have to, that's not good enough because that would be sort of it's called an algebraic loop if you have it closed like this. So somehow you have to give this some time constant, some state in order to make it well defined. So the way that we'll write it here is x dot equals negative x plus tanh of the inputs. And the inputs often have weights, weight 1, weight 2, weight 3. So in general, this would be a sum, but we'll just, in this case, it's just one input coming around negative x plus tanh wx. And that's the time derivative. So that's maybe the simplest model of the recurrent network. So yeah, I guess if everybody else is deep, this is shallow as it gets, but I like it. All right, so let's plot that function. Have you already done it in your head now? Once we back on to erase the board, you figure out where the fixed points are? Yeah.
Is that loop going for each of the inputs, or is it just for one?
Since there's only one output, we're just going to pretend there was only one input also. So the more general case would have multiple inputs, but in this case, it's just one. This is the entire equation. My output, you can think of as being this tanh plus wx, and I'll feed it right back. This negative x, if you want a justification for that, that's the leak rate of the neuron. So if you don't stimulate the neuron, it tends to lose potential over time. They actually make sounds too. The way people wire these things up is that neurons spike. So they're electrical potential. So experimentalists typically just wire them right into a speaker, and then when they're doing experiments, you hear tick 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 tick, and you hear this, they're not spiking. It's just a really good way to give feedback. The sad thing is though that if you were like, when the neuron dies, it goes, it's sort of, it's like you're broadcasting death to, to the room. Okay, so that's negative x. Tanh, like I said, it looks like a sigmoid, so tanh of wx, it's going to be bounded between, tanh by itself is bounded between 1 and negative 1. So this thing, when I add it all together, gives me some curves that look something like this. Okay? Now I'll erase my construction line. Okay, so what does it do? Where are the fixed points? Right, we know where the fixed points are. Which fixed points are stable? These, by the way, are not in arbitrary positions. They're actually at negative 1 and 1, roughly. I mean, asymptotes to that. Right, so this one's going to be stable because it's positive here, negative here. This one's unstable. This one's stable, right? That's memory, right? So you get that? So now we have a single neuron, which has sort of a latching mechanism. If I were to have additional input, I could kick it into some different state, possibly, and it'll stay in this state forever. Unless I were to have some extra input that came in and jarred the dynamical system, I could maybe get it over here and turn it off, if you will. And this bistable behavior that you see is sort of the potential foundations of memory. Okay? The interesting thing is that the exact locations of these, I was a little slippery when I said those are at 1. There's key points where they're at 1, and -1. That's the asymptote. But in fact, the slope of this curve, and so therefore the exact location of these fixed points, actually depends on the parameter w. Right? So with w, you get to change the height of the curve. This is where my multicolor come in. If I have a more shallow w, I can even get something like this, right? I can even get something like this, where I don't have fixed points over here and here, but I've turned it and I have a fixed point only in the middle. I can also have more aggressive parameters that do something more like this. Okay? So, as a learning machine, or soon as a feedback control designer, your job is to set the parameters, in this case w. These are different curves of w. I'm sorry, I hope that was clear. Right, this was like my w equals 1 curve. This is my w smaller. Did I say that right? So yeah. So for steep w, yeah, these are my big w's here. These are my smaller w's. Right? In the neural network world, the learning goes on by changing the strength of the synaptic connections. That's changing my w. So you can change the location of your fixed points, right? Or as a control designer, you can change the fixed points of your autonomous vehicle. Right? And that's our goal, is to figure out how to search these parameter spaces to design the dynamics of our life. Also note that if you make a big change, you can get into a completely fundamentally different regime where the number of fixed points is actually changed. So there's an important idea of bifurcations. Where as you change a parameter, you get a changing in the number of fixed points in the system. And this is one of the first cool things about, really sort of surprisingly different than linear systems, things about nonlinear systems. I mean, we already have systems that have multiple fixed points, which is a very nonlinear thing to do. But the idea that fixed points can just appear and disappear on changes in parameters is sort of a fundamentally nonlinear thing to do. And it's great that there's a whole literature on bifurcation theory and the like. A classic thing to do to shed some insight graphically into the system is to draw a bifurcation diagram. So I can draw as a function of my parameter w, let's plot where our fixed points are. Okay? So when w was very small or even negative would be the opposite, like this, then I said I had one fixed point and it was stable, so certainly if w is less than 1, I have a stable fixed point. The way I know that is that tangent of wx, the slope at x equals 0 is approximately w. Okay, so 1 becomes the key moment where my line of slope 1 and my line of slope 1 gives me something that looks like a tangent that comes in and kisses here and goes back. So I've changed, if I'm less than 1, I have something that is like this. If I'm at 1, I have something that looks like this, rides that. And then if I'm greater than 1, I have something that looks like this. Yeah? So something magical happens at 1. I get an explosion of fixed points here. They go off in 2 different directions. Okay? Like this. I actually still have a fixed point at 0 as these things evolve, but it becomes an unstable fixed point. So in the bifurcation diagram world, you draw dashed lines for unstable. And straight lines for stable fixed points. Okay? And actually, if you convince yourself here, if I go negative, I'll get even more and more stabilizing. So that fixed point is going to be a stable fixed point for arbitrarily negative w's. So this is called a pitchfork diagram, right? And actually, it's kind of fun if you get into the bifurcation literature. It's very colorful, right? So there's all kinds of names for diagrams of bifurcations. There's even a blue sky bifurcation. There's people who name things after themselves and whatever. Every time you watch some fixed points do something cool, you name it. Come up with a clever name. It's like naming a star or something. Okay, these things asymptote at 1 and negative 1. So again, now it's even more. Not only did I take a nominal system and understand what the fixed points were, now I took a parameterized system and I was able to draw a lot of information to the point where I think we really understand what's going to happen to the answer to that question of where's x going to be as t goes to infinity. This picture tells us a lot for any w, right? So these graphical tools are very, very powerful. So yeah, my OTAPs just had 1 parameter and 1 state, so that was easy to draw. I guess it'd be harder to draw it for a deep network, I admit. So that's an exercise for the reader. That's going to be like, how many networks? Standard recurrent network doing image, handwriting recognition or something has got hundreds of neurons and probably thousands of parameters, so it's harder to draw on the board. But the fundamentals are the same. Actually, that's a really, I joke, but that's a really fundamental point, right? So this is still happening inside those networks. And this is the mechanism that maybe makes them work. And your job in training a deep neural network is to put these in the right places, right? And it's really important to understand that. Okay, so let's think about the pendulum again. That was just to remind us that it's a general tool. But for the pendulum, if I think about having the pendulum with a constant motor torque input, maybe I can say U is the parameter I'd like to vary. So I'll start turning the current on my motor, and what happens to my fixed point? Can you think that through? So x dot, I've lost my equations, but it's x dot is bx dot equals mgl sine theta plus u, right? Minus mgl sine theta plus u. So u is just going to come in as a constant on top of this, and it's going to shift the whole thing up or down. Okay? So what does that do to the fixed points? Okay, the one you should probably not be surprised by is that if I apply a torque like this, then the fixed point at the bottom is going to go like this, right? But there's another fixed point in the system, remember? There's this fixed point up here, which is normally unstable, right? Where's that one going to go? Yeah, it's going to go over here, right? Where the torque I'm applying is holding me against gravity. It's still unstable, right? And then what happens? Let's see, if I keep turning up U, what happens? Yeah, I lose my fixed points. I have a bifurcation, and that is exactly how I threw a robot across the wall. I actually said the words, "Let me demonstrate instability," and then the robot was supposed to have limits, current limits, and torque limits. It was also supposed to be bolted really well to the table. That day, it wasn't, but it was unforgettable. So this is, you know, about as simple as it gets, but I want you to have intuition about these things. So, you know, I really like building little things that help you think about it. So, okay, you know, here's my pendulum. I've got a torque slider here at the top. If I apply a little torque, I can change the fixed point. It's going to move up just like we think, right? If I go the other way, of course, it's going to go the other way. It's exactly what you think. Now, this one's not very damped, but the fixed point analysis still holds. And we'll make sure we understand that that's true in a second. And as predicted, if I bring it up too high, what's the threshold?
MGL over B.
What is it?
MGL over B.
Yeah, MGL over B, right? So turns out L is 0.5 here, G is 9.8, M is 1, so it should be right around here. Oh yeah, there it goes. All right. My kids saw me doing this the other day, and they immediately tried to make it swing up. They were like, "Oh, look, I can go like this." It wasn't even. It's supposed to be a, you know, overdamped constant torque demo, and they tried to make it swing up. It's really hard. Don't waste your time on it. Okay, so I think it's fair to say that we understand everything there is to understand about a pendulum in molasses, which will serve you well. Yes? You guys feel good about that? So let's bring inertia back in. Yeah? Let's get to the second order version of the system. I needed that equation. That would have been perfect. I could have just used it. Okay, so the 2D graphical analysis now, or two-dimensional systems, let's say two-dimensional systems. Sadly, it already loses some of its magic, but we can still get a lot of intuition. So now I've got, if I think about this as I can think about any second order differential equation as a first order differential equation with two variables. If I say that the variables here are theta and theta dot, right, then x dot is theta dot, and then whatever works out over L squared minus b theta dot minus mgl sine theta. Right, so it's exactly the same as if I had a two-dimensional first order system or a one-dimensional or a one-variable second order system. How do you plot now a function that has two inputs roughly? I remember I plotted x dot versus x. Now I have x coming in is already two variables, and x dot, which I want to plot, is two variables. How do you do that on the blackboard? It's easier than the neural network, but it's slightly less clean than that, right? So the way to do it is to say, in this case, I've got theta dot, and in any particular theta and theta dot, I have two numbers to draw, so I'll draw it as a vector. Okay, and that's the state space diagrams. Is that clear? How that would be good? I've lost people at that point before. Okay, so let's draw the state space diagram, the phase portrait It's also phase space of the simple pendulum. Let's we just have to pick which ones we plot here. So I'll set b equals 0 and u equals 0 first, just to make sure we can get that. You can sort of convince yourself that if that's the case, so along the x-axis, where theta dot is 0, then my x dot is just 0 up here, and then g over L sine theta. So it actually looks like a vector which has no components in this direction. At any given point I draw here, I can plot that as a vector with some terms that are positive in y-axis only here. Oops, I'm missing a negative. I lost my negative sign. That would be really weird to do that. But it looks like a sine wave here, okay? And it looks like that same sine wave that I knew from before. And in the same place, we have fixed points in the same places here. I've got a fixed point there, because my vector is, the magnitude of that vector is 0, therefore that must be a fixed point. Anywhere, anything that appeared anywhere here that has a vector of size 0 would be a fixed point. But for second order systems, since I have theta dot here, that can only ever occur on this line, right? So my fixed points are on this line here and here, okay? Similarly, if I were to go up, if I keep, this was when theta was this is for theta dot equals 0, that was drawn along this axis. If I say theta equals 0, drawn along the other axis, then I get theta dot negative something theta, right? So I get something that just grows like this. And components only in this axis. And it turns out if you fill in the gaps, you'll see that these vectors over here kind of go like this. And these vectors over here kind of go like this. And if you were to simulate your system or solve the equations of the system somehow from initial conditions, you'd get solutions that follow those vector fields. That's why vectors are a nice way to plot these. They look like that, for instance. And similarly, there's rings of this that look like this. Okay, there's one really special one that looks like this. And actually, we'll go off this way too. And then inside here, you'll get rings that go over here. Up here, you'll see solutions that look like this. And similarly, solutions that look like this. Okay. Okay, so people feel like they've seen that picture before. It's sort of the eyeball of the pendulum. So it's a fairly famous face portrait of the pendulum. Is there a simple way to describe what these curves are? They are oscillations for sure, because they're going to go around like this. They're periodic solutions, right, that are going to last forever. They are defined, the thing that unites all of these points is that they are points that all have exactly the same total energy. This is the undamped pendulum. So if I wanted to plot this curve in MATLAB or something, then I could just set my total energy to some constant, I don't know, 0.5 or something, and I'd get a curve out that would be like this. Similarly, there's every one of these orbits is a curve of constant energy. This one that is particularly special is called the homoclinic orbit. Because it visits fixed points, unstable fixed points. Can you visually understand what that orbit looks like? So first of all, what does this orbit look like? That's just an oscillation like this around the origin. Okay, if I add more energy to the system, I get a bigger oscillation. What does the orange one look like? Yeah, right, so it's unstable here. You could sit there forever, but as soon as someone in the next room sneezes, it's going to go like this and come up and go back, you know, depending up to numerical accuracy or sneezing, it's going to land back at that fixed point again. You know, there's an orbit there. Okay. And then similar, this is the, you know, I threw a pendulum across the room regime. Now, the big question here is, well, this is not a stable fixed point. I think we can answer that quickly. Is this a stable fixed point? There's a right answer, but it's not a simple answer. Well, you could give it an obnoxious answer saying that's a bad question to us. That would be the right answer. Would be, please restate your question in something that I can answer meaningfully. Because in nonlinear systems, there are many different notions of stability that we'd have to clarify. Is that what you're going to say? Sorry, stealing the thunder. Well, we can use the words you were going to say.
I was going to ask what stable meant.
Oh, you would. That would have been the perfect question. I'm going to totally call on you next time. So, yeah, okay. So the question is, what type of stable? You know, which type of stable do you mean? And there's a couple different definitions, and there are implications of understanding those differences, even when you're thinking about much more complicated systems. So let me spend a few minutes to make sure you have those definitions. This sort of doesn't come up in linear systems theory, because linear systems have less possible behaviors. In fact, I should be able to convince you about that in 20 seconds, right? So for linear systems, if I even just a first order linear system, x dot equals ax, if I were to draw my x versus x dot, then what can that system do, depending on a, right? So I could have a straight line like this. I can change a to different values. I can have lines that go like this, right? Any of those are possible. But one thing I know is I'm always going to have a fixed point at the origin. And that fixed point is either going to be stable or unstable. And it turns out by all of our definitions, it would have satisfied. For any of the nuances of nonlinear stability are not present here. You're either stable or you're not. With the one exception, so these are the a less than 0 cases, right, where I've got negative slope. These are the a greater than 0 cases. What happens when a equals 0? Kind of a boring system, x dot equals 0, so you've got infinite number of fixed points, right? So these are things you've heard before. That would be the marginally stable case. Nonlinear systems are much richer than that, and I think the pendulum sort of showcases that. It's already sort of subtle. You know, is this fixed point stable? So the reason it's subtle is that if I start here and I ask, is it going to be here at time goes to infinity? The answer is no, right? It's going to somewhere beyond that orbit, right? But if I ask, is it going to go away from that? The answer is also no, right? So there's some meaningfulness in which it doesn't blow up and disappear and go somewhere else. So it stays in the vicinity of that fixed point. It just doesn't converge to it or diverge from it. So we need to be able to distinguish those different types of stability. So in nonlinear systems, there's actually many different ideas that come up in nonlinear systems. Nonlinear systems can do crazy things, right? So you can arrive at a fixed point in finite time. You can disappear to infinity in finite time. You can arrive fast, like in terms of exponentially fast. You can arrive asymptotically fast. You can never quite arrive, but still have something to do with stability. And so we need a language to fill in some of those details, to be more precise about our notion of stability. So in general stability, we talk about what happens from every initial condition, but local stability, the thing we've sort of been cartooning on the board of a fixed point, X star, is an important concept too, which is just, if I started near that fixed point, what do I do? Do I get closer to it? How fast do I get closer to it? Do I diverge? Okay? So let me give you the three most important ones. So there is local stability. So all of these are local in the sense of Lyapunov. There is local asymptotic stability. And local exponential stability. When we get back to trying to build stabilizing controllers, those are different things to ask of your controller design. And these are going to come up in, you're going to write the program differently if you want this versus this versus this. So it's not just culture, but I would do it for culture only. Stability in the sense of Lyapunov is the notion that I started near the fixed point, I'll stay near the fixed point, but it doesn't say anything about whether I actually converge to the fixed point. Okay, so how do I write that? The classic way to write, there's lots of ways to write that. You'll see us write it with Lyapunov functions later, but the one that's easy to write without any extra machinery is just to say, for every epsilon, small number epsilon greater than 0, there exists, be okay with exists a delta greater than 0, such that what I want to say is that if I started in a region near the origin, or near the fixed point, can I say if x0 minus fixed point, so that's a vector that's the distance between my initial conditions and the fixed point, and I'll take the length of that vector with that notation. Okay. If this starts as a small number delta, then I'd like to say then for all time, I will always be close to that. My distance stays small. Does that picture sort of does that math make sense? Does the notation make sense? That if I say, do you stay inside this epsilon? I should be able to choose any epsilon. Here's an epsilon ball in 2D. This is x1 and x2. I've got a two-dimensional phase-based plot again here. I'm going to say, okay, here's the game. I want you to stay inside epsilon at all time. I can pick any epsilon, any reasonable epsilon around a ball around the origin. You need to be able to tell me, sure, as long as you start inside delta, then you'll stay inside epsilon for all time. In the pendulum case, this is stable in the sense of Lyapunov, and you could actually choose delta. In fact, you must choose delta equals to epsilon. But in general, it could be that the system, if the system sort of had weird orbits like this or something like this that were very different in different directions, then delta could be a different size than epsilon. Right, starting inside, so this is a circle, and if my orbits are like elliptical or something, then I might have to pick a smaller circle to guarantee that I never leave the bigger circle. Is that fair? So they're not always the same, epsilon and delta. We'll understand that in detail. Okay, asymptotic stability says that the limit as time goes to infinity of x of t goes to x. But I'm going to get there as time goes to infinity. And exponential stability says that I'm going to get there, and I'm going to get there exponentially fast, right? That x of t minus x star of t. This is the distance over time, right? Can be bounded by some exponential. So these are for C and A positive. So there exists a C and A. There exists a C and A such that this is true. I should be able to, if I draw the curve of the distance between you and the fixed point, I should be able to draw it. It should live under an exponential curve. That tells me something about the rate. I mean, this A parameter tells me how fast I can expect to converge. So they're related, but they're slightly different. Some of the relations are sort of clear that if I'm exponentially stable, I will be asymptotically stable. There's a fun one that I'll leave for you guys to figure out. Turns out that asymptotic stability does not actually guarantee Lyapunov stability. It's kind of, the only example I know are sort of screwy examples, but they exist. Have fun, go find them. But like I said, so nonlinear systems can exhibit a lot of crazy behavior. So you could also have the case that I could converge in finite time, that I will arrive at the origin in a finite amount of time, and I can blow up and I can do all these things. And these things matter. They will actually change the equations we type into our optimizations later. Okay, so any more questions about that stuff? I don't need to just throw definitions, but the most important thing to me is that you appreciate the richness of things. As soon as you've got x dot equals something more than a linear function, both crazy things can happen, but also you have potential to make it do crazy things. As a control designer, it's an exciting place to be. So let's think now a little bit more about your opportunity as a control designer. I sort of said it in the nonlinear OTAPS example, that learning, or maybe control design, whatever, is you get to move the fixed points. Okay? But I really want you to come away with an even bigger view than that. I've got a big complicated vector field, right? It's probably too complicated, I should draw it again. Let me draw a slightly simpler version of it. And so I've got a vector field that does this stuff. But the vector field that I've got here, which in the initial case was just, I had vectors out like this or like this. It has one additional term that we zeroed out in our first drawing, which is u. We get an opportunity to add in a u. And you could make u a constant over time, not so fun. You could make u a function. If it's a controller, you can make it a function of theta dot, right? You have the power to change u. And remember, I abused that power in the feedback linearization example. I just changed the dynamics to be an upside down pendulum, right? You can't always do that, but you do have some power to affect the vector field. And that's the way I want you to think about control. So how does U enter in here? It turns out it enters in linearly, control affine way. If I have, say, limits on how much torque I can put in, and my motors have a fixed amount, I can take any one of these vectors and I can sort of add a little bit to it or subtract a little bit to it, but if I'm bounded, I can only do so much, right? So maybe my choices are sort of limited to something like that. But if I write it as a function, if I write a feedback controller that looks at the current sensor's state and then makes a decision instantaneously about what control to put in, then you get to shape the vector field, right? And I really want you to think about it like that. So, you have this vector field that was given to you, right? And you get to turn it into something different. That's what control is. Now, if I'm a humanoid robot, I've got a vector field that if the motors are turned off, well, there's a lot of friction in those joints. But let's say let's say it was just a loose pendulum robot, right? Then my leg wants to passively swing through, right? It turns out if you were to turn off Asimov's motors and give it a push, it would go, eh. Let's ignore that detail, right? So my leg sort of wants to do this. I've got a vector field that does its thing, right? And feedback linearization says, just erase this vector field and draw in one that's got straight lines and it goes exactly where I want it to go, right? And that's okay, but it's not so elegant. And it pays off, it hurts you when you care about battery life. It also hurts you when you care about robustness because you end up putting in a high torque and when the world wasn't quite what you expected, and your model was a little bit wrong, you canceled the wrong thing and robots blow up. Okay? Much better, I think, is to let physics do its work and just say, if I just were to, sort of like the Magician's Apprentice or something like this, you just kind of, I want to just touch it a little bit here, a little bit here, a little bit here, and I'm going to bend it with a little bit of work. I can come up with very elegant controllers that can change the dynamics of the system. And that's the way I want to think about control. Now, you can do that with algebra, and that's the way people did control for a long, long time. You can do it with RL, that's the other extreme, saying, that I'm just going to learn how to change the vector field. Most of this class is about understanding these equations, the structure in these equations, and writing optimizations to reshape those dynamics. Because you can often specify very complex things with pretty simple optimization problems. I think computation fills in the gap of controlling these very complicated things. My favorite example, like when I'm all done, I worked on fluid dynamics a little bit for a while, and people study this system, right? The dynamics of that are just ridiculous, right? It's a piece of paper, I just dropped it. The fluid dynamics are ridiculous, right? But they're beautiful and they're good, and if I really understood what was going on, I should be able to control them. So I, like to make the least practical mail delivery system ever or something. I'd like to be able to just blow it as it's going by and make sure it always lands exactly where I want. Right? To me, that's what elegant control looks like. It's something like that. Or the airplane, the paper airplane that made it to Harvard. That's the pinnacle of success, if we've got that. Cool, I guess I'm done a little early. But the problem set is released, and it's up. Thanks for your patience with the Dropbox, or with the Docker stuff. We knew it was going to be a pain in the butt. It was a pain in the butt, but thanks for just keep trying, and see you Tuesday.